Okay, so let's go ahead and cover curl and divergence. 16.5 curl. And we're talking about in 3 dimensions, whereas before we talked more about 2-dimensional. So early on in the course, we said that cross product is for rotational motion and dot product is for linear motion. So what this is going to do, we're going to use this with the gradient to get 2 new ideas. So the gradient, is the vector del over del x, del over del y, del over del z. Technically, it's called a vector operator. It's not a vector by itself, but we're going to write it as though it's a regular vector because it'll make it easier to write out the ideas that we're having. Curl then is going to be gradient cross f at any point x vector. And the div is going to be gradient dot f at some x vector. So this is just the shorthand mnemonic, which if you want to get really strict about logic, it's bad, but it's used so commonly that it's, as long as you understand what it really means. So divergence would be like we have a sphere and you have a point, it's everything going out in every direction added up. Whereas curl would be all the little 3-dimensional swirls, air currents and stuff going in circles. So I want to work out what these actually mean, because what is this mishmash of symbols? Well, let's work out what is gradient del or nabla cross f really mean. Well, f, we're going to say f is a function of x, y, and z, and we will write it as p of x, y, z I hat plus q of x, y, z j hat plus r of x, y, z k hat. So f will take R3 to R3. 3-dimensional input, 3-dimensional output. Now, del, we can rewrite this instead of writing it in, we can write an IJK notation as del over del x I hat plus del over del y j hat plus del over del z k hat. And so then if we want to say what is del cross f, well, if we remember how cross product works, the first row is I, j, k. Second row is the components of the left entry. So that del there is del over del x, del over del y, del over del z. And then the third one will be p, q, r. So if you work this out using our standard rules of expansion, you'll expand along the top, and then you'll do the determinant of the 2 by 2. So we'll get I hat, and if we take out the I part, take out everything in its row and column, we get this bottom right, del R del Y minus del Q del Z. Did I have that right? Yeah. Yeah, it's in our case where it's wrong in my notes, but what I'm writing here is correct. Okay. Minus j hat, and then it would be these two pieces, del r del x minus del p del z. And so you see what's happening. We're just saying, instead of multiplying these, we're just applying it. And then we have plus k hat. So if we cut out the k hat row and column, we get this. Del x on q. So we'll have del q del x minus del p del y. And if you want to think about what this means, this is saying this is what is happening in the the x direction. And you see what these are is everything that shows the interaction between y and z. R will be the z output, and y is the y input. Q is the output of y. Z is the input for z. So it's basically saying, how do things in the other directions go? So for instance, this last one, k, if we have the k vector, this piece here is talking about how x and y interact. So you would have something like this, a little rotation around it, around the k plus direction, or the z-axis. So what this is kind of saying is that in the k direction, we see what kind of rotation we have there. If we go in the x, or this is y normally, if we have z, y, and x. So if we were out here in the y, we'd see orbit like that. That would be the j component. It would be the x and z interactions. And in the x, we'd have rotation around that axis. Would be this, r and q, or the y and z. So the idea here, because in the two-dimensional case, it was just this last one in black. And that was because we were only dealing with x and y, so the curl had to be in the perpendicular direction to the xy plane. Each of these little mini curls here is perpendicular to whatever plane they're in. All right, so what I was saying is this is then the sum of three different two-dimensional curls in different directions. Notice the I is positive, J is negative, K is positive, but it's probably easiest just to plug it into this. I have a book I might recommend. It's called Div Grad Curl and All That. It's a fun little introduction to these things, or a little more in depth than we do in this class. But it has a line. It says that this is a formula that if you write out, no human could possibly remember all of it, or something like that. So that's why this cross product is useful. So let's do an example. Right. So f x, y, z will be xz I hat plus x, y, z, j hat minus y squared k hat. So like I said, I don't think I want to try to, find curl of f. I don't want to try to memorize the formula with all the complicated stuff. I want to just plug it in to a determinant. I hat, j hat, k hat. Del x, del y, del z. And then the three components here in order. xz, xyz, negative y squared. So we split this up. We get I hat, del y, del z, xyz, negative y squared. Minus j hat, del x, del z, xz minus y squared. Plus k hat, del y, del z. What's left over here? That's not under the k? xz and xyz. So xz, xyz. So let's go ahead and do this. Okay, so that gives us, for the I hat component, we'll have del y of negative y squared. That's negative 2y minus del z of xyz, so that's xy. Minus j hat, okay, now this is 0 minus del z of xz is x, plus k hat xz minus x. Did I do that one right? Hang on, I'm going to double check my work, make sure I'm not messing anything up. I did mess something up. Let's back up. What was this supposed to be? This was supposed to be del x del y. I don't know why I wrote del y del z. It's been a long several days, but anyway. All right, so del y del z, del x del z, del x del y. Okay, so hopefully some of you were screaming, "You did it wrong, Rob." Okay, so yz minus 0, because the y derivative of xz would be 0. So this ends up as, I'll factor some stuff out here, negative y 2 plus x I hat plus x j hat plus yz k hat. So that's the curl. Now, what this would say is that curl is not 0, at least not always. So f is not conservative. See, we said that in two-dimensional, that a conservative vector field is one where the two-dimensional curl is 0. Well, we just carried over three-dimensionals. If the curl is non-zero, then it's not conservative. And that has the same implications, that the integrals would depend on the path. Okay. I'm not going to go through the whole proof there. But yeah, there's a proof. It's in the book. If f is conservative, then there is some potential f. It says, that is to say, if capital F were conservative, then you could find potential little f. And if you were to plug in curl of capital F would be curl of del little f, which would be del cross del f. And you could work that out by hand, but it'll show that as long as your partials are continuous, so you can swap the order, it'll work out to 0. And then the contrapositive says if the curl is not 0, then f is not conservative. Though, as we saw in the previous case, in the previous day, it will cause problems if there's a hole in the domain. So like if we had a sphere with a hole in the center, that would mess everything up. So, all right, so that last example was not conservative. Let's see one that is. That's a bit of I'm spoiling the answer, but I could give you a problem like this. I could say xyz is y squared z cubed I hat plus 2xyz cubed j hat plus 3xy squared z squared k hat. And the question might ask, is f conservative? If so, find a potential function. And so testing if it's conservative is a good thing to do right away, even if you weren't asked. It might just say on the question, find a potential function if one exists. Checking if it's conservative is a good way to save some time, because if it isn't, then you don't need to waste time working out what the potential would be, because you know there isn't one. So that's I, j, k, del x, del y, del z, y squared z cubed, 2xyz cubed, 3xy squared z squared. Well, then that gives us I hat. Then we say, what do we get in this bottom right? The y derivative here would be 6xyz squared minus, go the other way. What is this derivative? 6xyz squared. Oh, we're off to a good start. Well, we got to check all three parts. J hat. Del x of this guy would be 3y squared z squared minus del z of this guy would be 3y squared z squared. Okay, plus k hat. Then we say 2yz cubed minus the y derivative here would be 2yz cubed. It comes out to 0 vector. Okay, so it is conservative, therefore a potential function exists. Now it's our job to track it down. So we take one of the three components. I don't think it really matters which one. Well, I mean, in theory, it never matters which one we start with. In practice, there will sometimes be cases where one is easier to do than the other. In this case, I don't think it will make much difference. So I'm going to start with x. I usually do if I don't have any reason not to. So little fx would be y squared z cubed. So then f would be the x integral of this, would be x y squared z cubed plus a constant function of y and z. That is, it's a function of y and z, but as far as x is concerned, it's constant. If we increased x, this c part would stay the same. Okay, so f sub y, we'll do the y derivative here. We will get 2xyz cubed plus, right, del c over del y. I don't want to use y or c prime because then I wouldn't know whether it's y or z is the variable. So I use this so I remember it's the y derivative. And that needs to equal this guy, 2xyz cubed. Okay, so del c del y equals 0. So that means that c is a constant with respect to y. So what this can really mean, if we say del c over del y equals 0, it means that c doesn't have y as a variable. So we could just go in here and delete this y. We'd say it's just a function of z. So now we do the z derivative. F sub z would be 3x y squared z squared plus del c over del z equals 3xy squared z squared. Oh, well, it's also a constant with respect to z. So this is just a true constant. And then, well, we might as well just say it's 0. So that's our answer. Now you can check this by just taking the derivatives. Take the x derivative, we get this. Take the y derivative, we get this. Take the z derivative, we get incompressible. So no curl makes it irrotational. No div makes it incompressible. And the basic idea being that if you're at any point, there's a certain amount going out, but there's also some coming back in. In net, it's 0, so the amount going out is the same as the amount going in. In fact, you might want to say that as a picture. Yes, I need to show a few pictures from the textbook because we want to be able to look at this visually. So I'm going to, let's open up here. Yeah, okay, I'm going to just, let's see if I can open the textbook on here so we can look at it together. All right, this will take me a minute if you want to fast forward while I get the book open. That's fine. I could edit this out, but that takes a while, and I know I should have had this prepared. It was in my notes, but it was a little vague, and so, well, bear with me. Like I said, the fact that you can just fast forward means you might not be listening to this. All right. Let's figure out. Okay, so this is the sort of thing that we could give you this on an exam or a homework, and it would be. So we want to say, what is the curl at these points here? Look at the point P1. We can see the curl at P1 is positive. It's P2, the curl looks more negative. We can see at this point, we can see there's sort of a counterclockwise rotation going around here. So the curl through this, we think is going to be positive. Then you can plug in the values here if you need to. Curl here is more negative because it's going in a clockwise direction. So positive, negative. And here, look at this point. The arrows are going right through it. It's not really rotating at all. It's just passing through. So the curl here at P is 0. So that's the idea. You look at the point and you say, is the motion there look like it's rotating counterclockwise? That's positive. Clockwise? That's negative. Or it's just going straight through it? That's 0 curl. What about div? Well, let's look at that. All right. So divergence refers to how much fluid is leaving. So if you look at P1, the arrows pointing at it are longer than the arrows going out. So at P1, divergence is negative. And you can see from this formula here, it's 2x plus 1, meaning if x is less than negative 1/2, it'd be negative. But you don't really need the formula. You can just look at it. Or at P2, the arrow coming in is smaller than the arrow going out. So that means here divergence is positive. So you can write that down as the rule. The arrow leaving the point is greater than the arrow coming in. That's a positive divergence. If the arrow coming in is longer than the arrow going out, that's a negative divergence. Over here, you can see at this point, it looks like the arrow coming in and the arrow going out are about the same. So that's 0. On a homework, I'm going to grade generously. So I would say, if it looks unclear, just explain why. So if you say, like, to me, it looks like the arrow coming in is longer than the arrow going out, therefore it's negative divergence, then I will accept that, even if to my eyes it looks like the other way around. All right. Now, the one last thing I want to say is how these formulas can also give us another way of writing Green's theorem. So we have some region here defined by a positively oriented curve, C and D. And we could say there's at some point, like this one, we can say there is a vector pointing out. We'll call it T for tangent. We've talked about the unit tangent before. And perpendicular to it is the unit normal vector. Or let's have it be the one going out. So we said that Green's theorem says that if you add up all around the outside, it's the same as adding up all the curls on the inside. So we can use Green's theorem here. We can rewrite it as the integral f dot dr equals the integral, there should be a c here, the closed path, of f dot t ds, or the double integral of del q over del x minus del p over del y dA, which turns into, this is curl, and this is curl in the k direction, the part of curl that's in the k direction. This is a two-dimensional curl. If you look back at the formula, this is the part that's attached to the k component. So we can rewrite this as curl dot of f dot k dA. So the idea is that that will give us, it'll sum up the curls in that two-dimensional version. So that's just the writing it in three-dimensional form rather than the two-dimensional form from before. As for the other one, what is n about? Well, the idea here is that we've got all these, every point, it has a bunch of stuff coming off of it. We can add what's called the flux, which is essentially just saying how much energy is passing through. If we put like a little screen here at this and measure how much is going through it. We'll do that, we could dot against the normal vector, because the normal vector points in that direction. So we would say the integral along C of f dot n ds equals double integral d of del p del x plus del q del y dA. Ends up as the double integral of divergence of f dA. And this ends up being what is called the flux. Alright, so that's pretty much everything we need. I may cover a few extra things that I want to just introduce next week. This is the sort of thing that, for instance, in a real analysis class, you'll go much more in depth in. But we're done with most everything new material-wise. So I will see you in class.